Okay, anybody have any homework questions before I start? Today I want to talk about Newton's third law and the third common misconception in this class. Who remembers the other two? So, common misconceptions so far. The first one was related to the bowling ball and feather video.
Oh, yeah, it was all.
Yeah, so gravity. So I'll say the things that are true. So gravity makes all objects fall at the same rate. And the only thing that makes things fall differently is air resistance affects them differently. Okay, and then the second one was sort of related to the other video we watched, the bullet being dropped and fired. Do you remember what the second one was?
So the bullet drop one, right?
That's right. And so the way I worded it was something like,
like horizontal speed affects how.
yeah, exactly. Horizontal motion. So again, I'm just saying the stuff that's true, not the thing that's wrong. But horizontal motion doesn't affect an object's fall. You could also think of this as horizontal motion doesn't affect the gravitational pull on an object. And so now the third common misconception. People often believe that in a collision, there's a winner and a loser. So imagine, like, say, a collision between a golf club and a golf ball. You think, like, the golf club wins that collision, the ball goes flying, and the winner in the collision applies a much bigger force to the loser than vice versa, you know. So the winner applies a bigger force to the loser than vice versa. Actually, at any instant when two objects are in contact, the magnitude of force that one applies to the other, how did I have this worded?
Every action is an equal and opposite reaction.
That is one way to word it for sure. The magnitude of force each object applies to the other is the same. Ooh, that's a good one. The magnitude of the force each object applies to the other, is exactly the same. This is Newton's third law. And exactly what you just said is roughly the way that it's worded in Newton's original manuscript. Something like, for every action, there's an equal and opposite reaction. Well, mathematically, that's not a very helpful wording, I don't think. But you've probably heard that phrase before. So really the way you want to think about it is whenever two objects are in contact, say you have body 1 and body 2 and they're in contact, the force body 1 applies to body 2 has the same magnitude as the force body 2 applies to body 1. Okay. So mathematically, the force vector on body A by body B is the exact opposite of the force vector on body B by body A. We've already seen this with pushing contacts. It's true with friction contacts. It's true with objects pulling on each other. Okay, so what does your intuition tell you with this stuff? Sometimes your intuition is right about this. Okay, so this is like creativity minute, relaxation minute. Okay, so now everybody close your eyes and imagine you're in a big grass field grilling something or whatever outside, and a ball, and, and this is important. You're out in this grass field and you're barefoot, okay? You're barefoot. You can feel the grass under your feet. And a soccer ball comes rolling in front of you, and you look up and there's kids like 20 feet away. And they're like, hey, kick this soccer ball back to me, you know? So imagine that, 20 feet. The kids are 20 feet away. So what do? You kick the soccer ball back, no problem, right? Okay, so now it's a new setup. It starts the same. You're barefoot, you're on the grass, you feel the grass with your feet. The ball rolls up, and you look, and the kids are 70 yards away, you know, almost a whole football field away, and they yell, kick the ball back to me. Okay, you're barefoot. And what's your first thought is like, if I kick that ball over there, it's going to really hurt my foot. Okay? And the reason it's going to really hurt your foot is because in order to kick a soccer ball 70 yards, you have to apply a really big force to it. And if you're applying a big force to a soccer ball, the soccer ball is applying a big force to your foot. Okay? So you totally like understand how that works. Okay, let me just write that down. So soccer ball thing. But there are other times when you probably don't think about it right, where it doesn't seem to make sense. The fact that this magnitude of force, there's a relationship between those two things. If one force goes up, also the force that thing is, the force that the other thing is applying goes up also, Okay, so sometimes your intuition is wrong on this. So for the second one, imagine a pro baseball player hitting a home run. Can I draw this? I don't know. All right, that'll have to do. Okay, so what happens when somebody hits a baseball really hard with a bat? After the bat and the ball make contact with each other, the ball goes flying, the bat doesn't. There's never a case where they make contact and the ball stays there and the batter goes flying into the stands, And so it's sort of natural for people to think, okay, the bat is applying a big force to the ball, but the ball is not applying a very big force to the bat, okay? That's a natural thing for people to think. But remember that the force that is applied to the ball is applied to something that weighs 1/10 of a kilogram or something. It's very light. It's not attached to anything else. And so say that there's a 5,000 Newton force of contact between those two things. If you apply a 5,000 Newton force to something that has a mass of 0.1 kilograms, you get a really big acceleration, okay? Now that same force is applied by the ball to the bat, 5,000 Newtons. But the bat has a lot of advantages. It's heavier than the ball. It's also being held by a person that is 1,000, 2,000 times the mass of the ball, okay? And then besides that, the person has their feet in spiked shoes dug into the ground, And so there is a 5,000 Newton force applied to the bat. That 5,000 Newtons just doesn't make the bat accelerate the way it does for the ball. So that's the way that this works. The forces between the two bodies are always the same in opposite directions. But that force doesn't always produce the same effect on the two bodies. And so thinking about this baseball thing, if any of you ever played baseball or softball as kids, well, you might not know this because when I played baseball, we still used wooden bats a lot of times. And so sometimes you'd break a bat, But when you're in Little League and you hit a ball and it breaks your bat, it just makes a little bit of a funny noise. And then you tap your bat on the plate and you can hear a rattling, there's just a little crack in there, So the ball applied an amount of force to the bat that caused a little crack inside. Then have you ever seen a bat broken in professional baseball in a major league game? It looks very different from that. The ball comes in, hits the bat, and the bat basically disintegrates into pieces. Pieces go flying, like players have to jump out of the way of the big part of the bat, whatever. So what's different? The difference is the batters are hitting the ball so much harder in professional baseball than in kids baseball. And that means that the ball is applying that much more force to the bat in pro baseball. And that's the difference between this bat that gets absolutely shattered compared to a bat that just gets a little crack in it, you know? So these contact forces, every time you have a pair of contact forces, if you can figure out the force that one of those things applies to the other one, then the same force in the opposite direction is the force that the other thing applies to the first thing. Yep.
What about if you like shoot a bullet at something and it goes right through it? Still applying the same amount of force?
Yeah, it is. So while it's going through, the board or whatever it's going through is applying a force that slows down the bullet. And the effect is that the bullet applies the force to the board. And you can imagine if you stood a board up just on its end, and fired a bullet into it, the board would tip over. Because as the bullet comes in, the board's applying a force this way that slows it down. That means that the bullet's applying the same force this way, and that knocks the board over.
Okay.
Yeah. Anybody else have any questions right now? So just remember that even when there's an extreme case of a winner and a loser in a collision, they're applying the same magnitude of force to each other. Yes?
So is that how like air resistance works?
Well, air resistance does work that way because air resistance, remember, is really made up of a bunch of little collisions of tiny little things. And so like if you have so if your car is moving through all these tiny little, think of them as tiny little balls, and that's what's slowing your car down. That's the air resistance, is these tiny little balls hitting your windshield as you're driving. But then your car hitting those tiny little balls makes them move a little bit this way, Like overall, it's moving this way. And that's why if there's a car right behind you, it's not feeling that. Like if you drive a full trip right behind the bumper of a car in front of you, you're not gonna use nearly as much gas for the trip because all these balls that car has been hitting are already moving from the collisions. And so you don't have to fight through those balls at rest. You're going with those balls that are already moving. Yeah. Any other questions? So we're going to do a couple lab activities to get used to this idea. And just remember, the basic idea is, for the most part, if you have a collision where there's a winner and a loser, the loser really is usually just the one that has less mass, because the same magnitude of force causes a bigger acceleration to something with less mass. Okay? The bigger things looks like they win the collision because like a 5,000 Newton force doesn't have a big effect on a semi-truck, but it does have a bigger effect on a little tiny car, My high school physics teacher drew this and I thought it was funny, so I still draw it all the time. When I was in high school, Mike Tyson was the heavyweight boxing champion, and our out-of-shape old physics teacher was like, I wish they'd give me a title shot. I guarantee if I fought Mike Tyson, I could hit him as hard as he hit me. And he drew this picture of like Mike Tyson's arm, the boxing glove, and then like his mangled face. But the idea is, okay, so a free body diagram of the glove would have a force from that contact this way. A free body diagram of the face would have a force this way. These two forces are the same, let's say 5,000 newtons, 5,000 newtons. So it is true that every time you get hit in boxing, you're hitting the other person just as hard. The difference is they're choosing where you get hit and you're not, so it's hard to win a boxing match by hitting someone in the boxing gloves, with your face. But the magnitude of those forces are the same. Okay, that's enough of that. Well, we've seen this stuff before with pushing contacts and stuff. Let me just do an example where, so let's say we have 3 carts that are in contact with each other. 1 kilogram, a 2 kilogram, and a 3 kilogram. And let's say there's a 20 Newton force this way and a 10 Newton force this way. And let's say we want to calculate the force applied to the applied to the 2 kilogram by the 1 kilogram. Well, first we have to isolate the whole thing and calculate the acceleration. It will be, but not, for the acceleration it will be, but the contact forces between the bodies, like the answer to this, is different than it would be if it was just 10 going to the right. Because you can imagine those two forces are having the effect of mashing everything together. Okay, so free body diagram of the whole thing. You have a weight force down of 58 point, I think that's 67. I think 58.67. Yeah, can you punch that in real quick? 6 times 9.81.
86.
Okay. And then there's a pushing force up. I'll call that N total. And then there's 20 newtons this way and 10 newtons this way. And Newton's second law says 20, 0, plus 0, negative 58.86. Plus 0 N total. Plus negative 10, 0. Is equal to the mass times the acceleration. Is this moving along x or y? X, so I'll call this A0. The x equation says 20 plus 0 plus 0 plus 0 is equal to 6a. And so a, 0 plus 0 plus, this one should be negative 10. So a is equal to positive 1.6 repeating meters per second squared. And so the acceleration vector is positive 1.6 for x, 0 for y. Okay. Well, now we want to calculate the force that's applied to the 2 by the 1. So the first thought is isolate the 2 kilogram thing. But that wouldn't work in one step because there would be 2 unknown forces on the 2 kilogram. Let me just draw that free body diagram. Okay, so you'd have a weight of 19.62. You'd have a pushing force N2. You'd have a pushing force this way, R1, and a pushing force this way, R2. That's 2 unknown horizontal forces. And so that means that the x component of Newton's second law would have 2 variables in it, and you can't solve for it. So this won't work. Because there's 2 unknown horizontal forces. So instead, I'm going to isolate the 1 kilogram thing. I'm going to calculate the force on the 1 by the 2, and then I'm just going to use Newton's third law to get the force of the 2 on the 1. Okay? So instead, I'm going to do a free body diagram of the 1. There's a weight force of 9.81, a pushing force of N1 from the ground, a force of 20 newtons on the left side, and a force over here, I'll call that R. It's really the R1 from up there, so I'll put that in there. Okay, so Newton's second law says 20, 0, plus 0, negative 9.81, plus 0, N1, plus negative R1, 0, is equal to the mass times the acceleration vector. And so the x equation says 20 plus 0 minus R1 is equal to 1.6 repeating. And so R1 is equal to 18.3 repeating newtons. This right here is the force vector on 1 by 2. Once you plug in that value for R1. And so the force on the 1 by the 2 is negative 1.60, or in the negative x direction with a magnitude of I wrote that wrong. This should be negative 18.3. That's in the negative x direction with a magnitude of 18.3 repeating. So by Newton's second law, or by Newton's third law, I mean, the force on the 2 by the 1 is negative 1 times this vector, the opposite of it. So 18.30. Or if you want to visualize it, that's in the positive x direction with a magnitude of 18.3 repeating. Okay? Any questions about that? Okay, well, that's the end of talking about Newton's laws. I would like to just take a little time for the rest of class and give you some problems to work on, and you can work together on them or ask me questions if you get stuck, and I'll give you time to do it, and then I'll do it and just give you some practice with this. Okay, first example problem. Let's say we have a block on an incline of 20 degrees. This block has a mass of 10 kilograms. At the instant shown, it's moving down the ramp. Calculate the acceleration of this block. The coefficient of friction between the block and the incline is 0.2. Is equal to the mass times the acceleration. Is this moving in the x or y direction? The hanging one. Y, yep. So I'll write this as 0a. And so my first equation says t minus 9.81 is equal to a, and I'll set that aside. And now I'll go to the cart. There's a weight force of 29.43. There's a pushing force from the ramp. There's a pulling force from the cable, and it's the same cable as the other body, so I'll call that T. In this coordinate system, the weight force is like this, and this angle is 40 degrees. So the angle we want is 270 plus 40. So 310 degrees. So Newton's second law says 29.43 times the cosine of 310 degrees. 29.43 times the sine of 310 degrees. Plus 0n plus negative t0 is equal to the mass times the acceleration. And now is the last tricky step in this stuff. So if the 1 kilogram object moves an inch in its positive direction, which way does the 3 kilogram move? Down. So is that positive or negative x? Positive, yep. So we're going to write this as, so a positive y motion of the 1 kilogram corresponds to a positive x motion of the 3 kilogram. So I'm going to write this as positive a0. I'll use the x equation here. What's 29.43 times 3 cosine of 310? What?
18.29.
Positive 18.29 minus t is equal to 3a. So our system of equations says t minus 9.81 is equal to a, and 18.29 minus t is equal to 3a. The first one says t is equal to a plus 9.81. Substitute that into the second one, and you get 18.29 minus the quantity a plus 9.81 is equal to 3a. So 18.29 minus a minus 9.81, because you have to distribute that negative through the parentheses, is equal to 3a. And so what's 18.29 minus 9.81? 18.29 minus 9.81?
8.48.
So 8.48 is equal to 4a. And then, oh my gosh, that's really easy to do in your head. So you get an acceleration of 2.12. Okay? So now, the last step, don't forget the last step. If it asks for an acceleration vector, make sure you give your answer as a vector. We want the acceleration of the hanging mass. So we want to plug that value for a into this equation. And so what we get is a is equal to 0, 2.12. Or, in other words, the hanging mass is accelerating up with a magnitude of 2.12 meters per second squared. Okay, any questions about that? All right, well, let's call it for today, and then we'll get into circular motion on Monday. So yeah, remember, there's no school Wednesday through Friday of this week, and there's also no lab this week. So I don't want to see any of you. Actually, I do have office hours tomorrow, and I can see you there if you want, but.
There's someone Tyson back here, and they just came out and played if you're interested.
Oh, really?
Yeah, it's on food.
Did they show him punching my physics teacher?
Well, other people.
Yeah, other people, yeah.
And by you that you're on.
Yeah,
But it's
that's funny. Uh-huh.
So it's pretty cool.
Okay, I'll look for it. I do like that
I
stuff.
watched it last night, which is funny when you brought it up.
That is funny.
Just watched.
That's really funny.
Okay.
It's funny too. I just like last week or a couple weeks ago watched a documentary on Evander Holyfield. So their lives are sort of entwined forever now. Have you seen the picture like of them joking around with Evander Holyfield pretending to bite his ear and he's like, ah?
Oh no, I didn't see that.